So this is question number 9 of chapter number 8, which you can find on page number 194. In this question, we have a synchronous motor which is taking 50 kilovolt ampere at 11 kV with a power factor of 0.9 leading. The question asks us to calculate the generator's terminal voltage, the terminal voltage of the generator, and it wants us to find the currents in the generator, transmission line and the motor. So the questions ask you to find the terminal voltage of the generator and the transmission line current over here, the motor current which is on this side, and the generator current. The information given to you about this system is that the generator has 0.8 ohms reactance, the motor has 0.23 ohms reactance. The transformer number 1 has a reactance of 400 ohms, which is referred to the low voltage side. So between this side and this side of the transformer, the low voltage side is this one here. And the second transformer has a reactance of 21,780 ohms on the high voltage side. So if you look at the two sides of the transformer, high voltage side is the one which is connecting to the transmission line. Because you know, for the transmission line, we step up the transformers usually. So this side will be the high voltage side. So if you wanted to draw an equivalent circuit of this system, you will draw the reactance on the transmission side, which is the high voltage side. The other information given to you about the system, you can see it under these components. Remember, whenever there are more than two information given to you about a unit in the question, you have to be careful that the rating, this value of apparent power given to you in the question is actually the rated apparent power, which means that this is the apparent power with which this motor was designed to work on. It is not important, it's not always necessary that the question asks you to solve your questions at the rated values. Because if you look at the motor, it is designed with an apparent power, rated apparent power. Rated means the power with which the motor has been designed. It is 80 kVA, but the question says that it is taking 50 kVA. So some of the students may get confused that which value should be used in our question. So of course you will use this value here, because the motor is actually taking at this moment 50 kVA, not 80 kVA. The same goes for the generator and every other information given to you about this system. These are actually rated values, above which the components will actually create problems. So they were designed to work at this value or less than it. Okay. Now, first of all, we will calculate the motor current. The motor current can be calculated by simply dividing the kVA over the voltage, the line-to-line voltage. So the formula is simply the apparent power, which is given in the question as 50 kVA, divided by square root of 3 times the line-to-line voltage of the motor, given to you in the question 11 kV. You will get the motor current of 2.62 amperes. The angle of this current can be calculated by taking the cosine inverse of the power factor, which is leading. So 25.84, and your motor current will come out to be 2.62 ampere with the angle of 25.84 degrees. Now, if you look at the second transformer, the turns ratio of the second transformer over T2 is 132 over 11. We call it A, so it comes out to be 12. Now the motor current, if you refer it to the high voltage side of the transformer, because this is where the motor current is. So if you refer the same current to this side, there will be some changes because of the transformer. So that change is actually dividing it by the turns ratio 12. Because remember, this is a step up. This is a step down transformer. If you look it from this side to this side, this is a step down transformer. It is going to the load. So this side will have a high. This side will have a lower current because this is the transmission line side. So you always divide it with the turns ratio. So the current will be divided. It is 2.62 on this side. You divide it by 12. You will get 0.218 with the same angle. Because we assume, if it's not given to you in the question, we assume to be Y and Y, or this will be a Y-Y connection. That's why the angle will not change here. So this will be the motor current referred to the high voltage side of the transformer. High voltage side is this side. So this will be the current, and this will also be the same current in the transmission line, because if you see that this is a series connection, and whatever current you will have on the high voltage side of this transformer will be the same as the current in the transmission line. So ITL will be this 0.218 angle 25.84 ampere, and this same current will also be on the high voltage side of T1. And if the turns ratio, what about the turns ratio of the first transformer? It is 132 divided by 20, it is 6.6. Now this same current, which is 0.218 angle 25.84, which is on the high voltage side, of our first transformer, if you refer it to the low voltage side of the transformer, now it will increase, the current will increase, because the voltage is stepping down. If the voltage is stepping down from right to left, it means the current will increase, current will step up. So you will multiply it with 6.6 to get the current. So after multiplying it, this current will be 1.44 angle 25.84. This is referred to the LV side, or low voltage side of your T1. So if you want to move the current from this side to this side of the transformer, you must multiply it with the turns ratio, as simple as that. And this current will be the same as the current in the generator, because there is nothing after that. It's simple series connection. So the IG, or the current in the generator, will be 1.44 angle 25.84, the same as the current in the low voltage side of our transformer number 1. So these were the three currents that were needed in the question. We have calculated them. Now we will try to calculate the terminal voltage of the generator. To calculate the terminal voltage of the generator, we will do the same steps, and we will go from right side to the left side, but now we will go in terms of the impedance. So the impedance of the motor can be calculated by simply dividing the line to line voltage, or the line to line voltage divided by square root of 3 to change it into phase voltage. So the phase voltage divided by the phase current, you divide both of them, you will get the impedance of the motor. This impedance of the motor is over here. If you want to take it to the other side of the transformer, you will actually have to increase it. So you have to multiply it with A square. So this impedance of the motor, if you want to take it to the high voltage side of transformer number 2, you will have to multiply it with A square. A being the turns ratio of transformer number 2. Which we already calculated to be 12. So 12 square, which is A square, times this impedance. You will get this impedance of the motor, but now it is referred to the high voltage side of T2, or transformer number 2. This is the high voltage side. Now after converting this motor impedance and bringing it to the high voltage side of the transformer, the next step is to combine these impedances. So what we will do next is that in the question, the impedance or the reactance of the second transformer is given to us, but it is on the high voltage side, which is this side somewhere over here. So if you wanted to draw the equivalent circuit of this system, it would have been an impedance on the high voltage side, which would have been 21,780. So now, because we have converted the motor impedance and we have brought it to the high voltage side, all what is left is to just combine them as if they were in series now. So we will combine it with the reactance of the second transformer, plus the transmission line also has a very small impedance, which is 2 plus J50. If you look at the question, the impedance of the transmission line is also given, so we just add them up, all of them. But we will not add the reactance of the first transformer. Why is that? Because it is not given to us as high voltage side. If you look at the reactance of the first transformer, it is given to us as 400 ohms, but on the low voltage side, on this side. So because it is on this side, we cannot combine them, or we cannot simply add them up yet. We can only add the motor impedance, which was transferred or referred to this side, and then we added to it the reactance of this second transformer, and then we also added to it, because it is in series, we also added the transmission line impedance, this plus this. You can see it over here. We combined all three of them, and then we got the Z total up till now, or you can call it as subtotal. The impedance subtotal, it came out to be 34,000 and 340,111 with this angle. Now this is the impedance up till this point here. Again, we have a transformer now in front of us. So this impedance is up till here, this Z total. We have to jump, or we have to refer this impedance now to go to this side. So what do we do now? Because we are going to from the high voltage side of the transformer to the low voltage side, we will actually divide it with the turns ratio squared. So we will divide this impedance with the turns ratio squared, and then we will get the Z total from right all the way up to this transformer, but referred to the low voltage side of this transformer. So all of this impedance combined and referred to the low voltage side of this transformer, it will come out to be 7,808 with an angle of minus 22.53. Now when you have referred, or you have transferred all of this impedance to this side of the transformer, now you can add them up in series, because the question says that the reactance of this first transformer is 400. Because it's reactance, you will automatically put a J here. So the reactance of the first transformer is J400. We just add it to the total that we just calculated up till now, referred to the low voltage side of the transformer 1. You combine them, and then you will get this total impedance up till this point here. By adding it, you will get the final answer of the impedance to be 7,663 with this angle. Now when you have referred all of this impedance from this side to this side, and then combining them, then again converting it from this side to this side, and then adding the low voltage side transformer reactance, now you have the total impedance referred to the generator, or in other words, you can say that this will be the impedance that the generator is seeing on this side over here. So this impedance simply multiplied with the generator current that we just calculated in the previous step. If you multiply them with each other, you will get the phase voltage of the generator, which will come out to be 11,035 with an angle of 6.1. So just multiply it with square root of 3, and you will get the terminal voltage, because terminal voltage is the one that you will see when you when you try to measure it with a multimeter across the terminals of the generator. So across the terminals is always the line to line voltage. So you will convert this phase voltage by multiplying with square root of 3, and you will get from 11,000, you will get it as 19,000 or 19.11 kilovolt, the generator terminal voltage.